Okay, so follows from what we did before, and I haven't connected all the dots. And then we will connect them, but you know, that's enough dots to connect for one day. Okay? It follows that delta L equals tau net delta T, okay? Which is just analogous to, I say just like, I should have said analogous to, but this, which is the impulse momentum theorem, right? Okay? Now, if F net delta T is impulse, what do you think tau net delta T is? It's not going to have the same units because tau has units of force times distance, right? Okay, from what we just said, think about it. But that's your net torque, right? And torques apply to angular motion, right? And angular dynamics, and angular energies, and so angular kinetic energies, and so forth. So, this quantity here is what we call impulse. This quantity here we call angular impulse. And these are important statements because since two rotating objects or two objects in a rotational situation that interact exert equal and opposite forces in each other, and about any given axis, that means they exert equal and opposite torques. Since they exert equal and opposite torques, well, it's going to turn out there's no change in what we call angular momentum. Okay? In other words, the tau net delta T for one is equal and opposite to the tau net delta T for the other. And I haven't defined it yet, or the term. It's angular momentum. Okay? Okay, well, turns out then, to change the angular momentum of an object, you've got to have a net torque acting for some time, right? Angular momentum is it's maybe the most difficult concept in first semester physics, okay? Because you have to think about all the vectors in 3 dimensions and stuff like that. Right now, we're not worrying about the 3-dimensional aspect of it, but we will soon. So we want to ease into the idea of angular momentum, okay? So we accept this, okay? We'll connect the dots later. Now, L is angular momentum. You need a net torque to change it. Okay? Is there a net torque on this satellite? Relative, of course, to the center of the Earth, which is your axis. Well, what's the direction of the force exerted on the satellite?
Toward the center of the area?
Huh?
Toward the center of the area?
Yeah. So, here's your force, here's your net force. And that's, you know, your F net is equals G big M times little m over R squared multiplied by the radial vector over its magnitude, right? And if you don't totally recognize that and haven't thought about it, you really need to, okay? Okay, well, so here's your F net. Now where's your R vector? R is your radial vector, sort of. It's a vector from the axis of rotation to the point of application of the force, right? So the R vector right?
Is that G, M1, M2?
I got big M and little m. I'll use it interchangeably. You got two different masses, right? Doesn't matter if we call one the aardvark and the other the anthill. It's two different masses. And it's implicit from the form what it means. And you've seen, I'm almost sure in assignments I've used this notation, and nobody's emailed me to say, what the heck does that mean? So I assume you recognize that because of the G in the R squared and the unit vector over here is the same thing I wrote down with an M1, M2, right? And generally when one mass is much bigger than the other, as in a planet and a satellite, or star and a planet, or star and a satellite, the big M will be the one with the greater mass, little m will be the other one, and we assume that little m is a whole lot less than big M. It's all kind of implicit in this situation, okay? And when it isn't obvious and implicit, then, we say more in our statement, okay? The statement of a problem, we clarify it. Which goes against my nature, but I do it anyway, or try to. Okay, make sense? Okay, now my question is, what's the torque?
F.
What?
F net times change in time times the.
Now forget that. Just from what you, forget all this for the moment. Remember this, because you got to know where this thing's pointing, right? And incidentally, I left the negative sign off here, okay? And that's why I didn't recognize I left the negative sign off, right? Okay, well, no, because you're not that familiar with it yet. Okay. Okay. Look back at what we did earlier. How is the R vector related to the net force vector? Is it like the green one, the orange one, or the yellow one?
Orange.
Huh?
Orange.
Nah. Somebody pick another one. Let's flip a coin.
Green.
Huh?
Green.
Nope.
It's like the white one, since it's a force acting directly towards the center of center of the.
Yeah, F net and R are acting along the same line, right?
No, the green.
Now, it's not white, it's yellow, but it depends on your color vision. This one acts along the line of the R vector, right? Because the R vector goes from here to here. So what's the torque?
0.
0. Since the net force has no component perpendicular to R, which is maybe the easiest way to see it, okay? But we can say okay? Or we could say F net dot R is 0, right? And that's totally wrong. Actually, F net cross R equals 0, and we can't even really talk about that until you review this cross product, okay?
Would we have done the cross product on that funny shape one over there?